project. They did this actually a few years ago. They installed 16 solar collectors on their roof to heat their domestic hot water. And how this system works is you've got your solar collectors which are absorbing the heat energy from the sun. So they're collecting as much heat as possible. You've got a fluid that you're circulating throughout there that takes that heat and transfers it down into the building. This hot fluid enters your storage tanks, you bring your cold water in, and then you have a coil or a heat exchanger set up where you transfer the heat from the fluid that you're collecting up here to the cold water. So you're using two different fluid streams. There's no cross-contamination. Cold water gets circulated, goes into a storage tank, and that's what you use for your facility. It's pulled the energy out of this circulating fluid, so you have cooler fluid going back up to absorb more heat energy. So that's the system they've got at Saskatoon Lake Power. They don't have a good monitoring system, or they had a monitoring system, it broke down, and they decided not to invest the money to put it in the capital to rebuild it. So we can't get exact energy saving figures for it. But there is the result that they used to have two hot tanks that they needed to have operating all the time. Now they only need one. So therefore the system's paying for itself. We just can't exactly quantify how well. So that leads to one of our projects, which is the solar hot water heating that we're doing for our civic swimming pools, our indoor swimming pools. And this system, the solar hot water, is very good for swimming pools. If you compare it to the domestic hot water system that we just looked at. So here's our domestic system. For the swimming pool, very similar. You've got your fluid that you're taking the heat off your solar panels. You take it to a heat exchanger. You're heating up water, taking it into the pool. You've got a constant flow of cooler water coming back into the exchanger and doing a loop that way. The primary advantage, right off the top, is in storage tanks. So this system, you heat up water, you store water, you use it when you need it. For pools, there's no tank. The pool itself is the tank, and that's constantly circulating. So you don't have this changes in demand. So that automatically adds a certain amount of efficiencies to the system. The next thing is, for a hot water system, you want 55 degrees Celsius water. For a pool, you don't want to be swimming at 55 degrees Celsius. 30 degrees is kind of the max of anything you're going to be looking at. Now, when you're heating up water, for each degree, the hotter you want to make it, the more energy it takes. So if your target temperature is lower, there's actually a much higher efficiency in that sort of system. So just for the fact that we don't need to go as hot, we can get a more bang for your buck as we implement the system.
Chris, what do you do through the night with the pool? You just shut the system down?
I believe right now, it depends on the pools. I believe at the Harry Bailey Aquatic Center they keep everything at the exact same temperature all night long. And part of that is, for whatever programs, the cleaning staff can't get into it until late at night, and then the cleaning staff's in there for a couple hours. So you've got actually occupants until 3 o'clock, 4 o'clock in the morning, and then you're starting up again at 5, 6 in the morning. So there's not much savings to letting it cool off.
But do you keep running if you keep running your fluid through your solar system, it'll cool the pool at night?
Oh, there are monitors, there are temperature sensors on that system. So if it's not getting the energy out of the solar system, it's not.
Well, it's probably still circulating, but it'll be closed, right? Closed loop.
Yeah, the glycol. Yeah, that will always circulate. It will be circulating the glycol all the time. They'll just be cutting off the heat transfer. Like they won't bring in the pool water.
And is there a backup heater?
Yes.
Okay.
And the point is, actually, you don't want to design one of these solar systems to do 100% heating oil. I'll get into that shortly. This is just a cut cross-section of what the hot water solar panels look like. The main thing is this black metal, which is absorbing the sun's energy, getting really hot. And underneath that you've got a copper pipe, which has your heat transfer fluid. Usually it's some sort of glycol fluid. And so you collect the heat on this metal plate, transfer it to the fluid that's flowing through this copper pipe. You've got a tempered glass on the surface to protect the panel. And you've got insulation to whatever energy you've got into maintaining it in there, isolating it from the ambient conditions. So this is the Harry Bailey Aquatic Center, and this is how we've set up the collectors on the roof. We've got 72 collectors down. One thing was, we're focusing only on this smaller building, the 25-meter pool. At Harry Bailey, it's kind of a unique situation. The main building, or the main pool, is actually owned by the province through SciAst. The smaller building is something the city built as an addition to it. Now, we operate the whole facility, we lease this from the province, but to do any kind of capital infrastructure adjustments, we need provincial approvals, and there's just too much bureaucracy, it wouldn't fit our time schedule. So this time we thought, well, let's just focus on the city's material. Let's use that. In the future, if we can prove the monetary savings, we may approach the province and say, hey, let us put in panels to keep that pool as well. But for now, we're just focusing on the smaller pool. And this is the Lost Heights Civic Center, the other place where we can install these panels. That's the pattern that we've got on the roof, and here we're using 90 collectors. And one thing you'll notice is that we're skewed. For panels to be working at optimum efficiency, they should be facing basically due south. Because of the different infrastructure we have on the roof, we had to kind of adjust the angle to maximize how many panels we could put up there, where they could be put up there, without having to do any kind of adjustments to the roof itself. So we're about 11 degrees off of south. What does that mean? Well, in the morning when the sun's over here, we're less efficient. In the evening, we're a little bit more efficient. Overall, there's not that much of a difference. I think they're predicting to be like something like $20 a month difference in fees. So it's really negligible. But there is a savings if we could have got that perfectly south. Here's a picture of the lift of the installation that we were doing at the Lost Heights Civic Center. A couple things you want to notice about this. First of all, the angle of the panels. Again, for maximum efficiency, it depends on the time of year where the sun's at, but in general, they'd be a little bit more efficient if they were a little bit flatter, a little bit more. But they're up at this angle so that the snow won't build up on them, the snow will fall off, as well the rainwater will wash them so that they're the lowest maintenance. In fact, we don't expect to ever have to actually go up there and clean them. Just set them up and leave them. The way we're lifting them on the roof, well, we can actually remove them that way as well. They're not structurally attached to the roof in any way. So the roof still has its complete membrane, where there's no chances of leakage. Now the issue is, well, if they're all freestanding, what happens, like wind? Can wind blow them over? Well, actually, we've got them attached to this frame. We have a continuous frame all the way around. So in order for them to blow over, the whole frame would have to pick up. And we have strong winds, but we don't have that strong winds. So it's very, very strong that way. And by not attaching it to the roof, if they have to do roof repairs or some kind of adjustments, well, you get a crane for a day, you pick up the panels, you set them down in the parking lot, you do whatever you need for your renovation on the roof, pick the panels back up, put them back up. It's a one-day install to get the panels up, take it down. One other thing you might notice is the spacing. There's actually quite a bit of space between this row of panels and the next one. And again, you think, well, if you put them closer together, you could put another row in there, make it more efficient. If you think of, this is designed for kind of the winter heating load. In the winter, the sun's lower on the horizon. So if you look, the sun, as it shines above one panel, actually just catches the bottom of the next one. So if you had them closer together, you actually have a shadow on the bottom of the panel, lessening its effectiveness.
So you have no shadow?
Right now, we have no shadow.
Okay.
I believe probably on December 21st, there probably will be a bit, but I know clarify that, depends on the time of day too, because when the sun's on the close to the horizon, of course you're going to get certain shadow. So we're looking at 1 o'clock, no shadow. That's kind of the main design. So if you think in the summertime, sun's higher, so actually the sun will come down and the heating impacting here, so you think, well, this isn't designed very well for the summer. But in the summer we have less heating demand. It's in the winter that we really need to supply energy here, so let's maximize our efficiencies for the winter installation. Again, best bang for your buck, makes the system mostly economical, get the best return on investment. So, expected performance. So these have just gone in. Lawson went up 2 weeks ago, Harry Bailey I think was just installed. Actually, I think it was this weekend. I think it was last Saturday I think we lifted up. So total budget for both projects, $224,000. We're expecting to pay for itself in about 11 years. The Lawson, we're doing about 25% of the heating for the pool. Harry Bailey is about 20% of the heating load. And that's the average for the year. In the summer, that crops up more around 35% of the heating load. The winter drops down to 15% of the load. And again, if you think that when you're heating